Hello, and welcome to chapter 4 of our lecture note discussion. In this chapter, we are going to introduce you to what we call probabilities. The first question we usually ask ourselves when it comes to probabilities is, what is probability? Probability, we are basically looking at uncertainties. You see, often in statistics, the question we tend to ask ourselves is, if a specific method works, how often will we see the same result when we apply the same method? Think about it this way. A manager makes a decision and the decision results in a very good outcome. The question we ask ourselves is, how often will we get the same outcome when that decision is made? And that is what probabilities are about. Now, for those in the sciences, you may think of probability as this. Think of a nurse giving a certain medication to a patient. The question the nurse may ask herself or himself is, how often will I see the same result when I administer this medication to another patient? Now, probabilities are applied in many different fields. Now, but because this is a business statistics field, let me give you an example of how managers use probabilities to make decisions. You see, managers often base their decision on uncertainties. What are the chances that sales will increase if the method of increasing prices is applied? And so here we are looking at the possibility that we will increase sales if we decide to increase prices. And so here increasing prices become the method, and then sales increasing becomes the result, right? And so probability is basically looking at how often will we get this result if this method is applied. What are the chances that a new assembly method will increase productivity? And so here, the method is the new assembly method, and increasing productivity is the result we're looking at. And so with probabilities, we are actually looking at chances that we will get the same result when a specific method is applied. Now, probability is usually a numerical measure, which means probability is just a number that we assign to the likelihood of an event occurring. It's important to note that probability is always between the number of 0 and 1. What does this mean? It means that probability can never be less than 0, neither could it be more than 1. And so if somebody assigns a negative value for a probability or the chances of an event occurring, that is not possible. Neither can we assign a positive number greater than 1 as the probability of an event occurring, which means probability actually ranges between 0 and 1. It can never be less than 0. It can never be more than 1. I was watching a video one time, I think it's one of those reality shows, and a guy was asked, what are the chances that you will be the winner in this competition? And he said, I am 120% chance that I will be the winner. Probabilistically, that is wrong. That is not a value we assign probability to. Probability can never be less than 0. It can never be more than 1. But it's important to know that as the probability value you assign to an event occurring nears 0, that is an indication that the event will not occur. And as the probability gets closer to 1, it indicates the certainty that the event will occur. And so let's say you are a member of a team, and your team has a competition coming up, and you are asked to assign a probability value to the chances that your team will win the competition. As the value you assign gets closer to 0, it's an indication that your team is going to lose. As you assign the value closer to 1, it's an indication that your team is going to win. When we look at the chances that both events can occur, that is, you can lose or you can win, we assign the value of 0.5. And so here we are looking at a 50-50% chance that you are either going to lose, getting closer to 0, or you are going to win, getting closer to 1. So with probabilities, we are looking at this range of values between 0 and 1, where 0.5 is that either of these two events could occur. Now let's talk about random experiment and sample space. Before we can generate or before we can assign a probability value for an event occurring or something happening, we need to perform a random experiment. A random experiment basically is a process that generates a well-defined experimental outcome. And so everything we do, any activity that has a result, could be described as a random experiment. Now, why do we say it's random? Because we are looking at the possibility of an outcome in a list of outcomes occurring. Now, all experiments or all activity or all events have what we call the sample space. The sample space basically is defined as the set of all possibilities, the set of all outcomes. And then a specific outcome in our sample space is called an experimental outcome or sample point. Let me give you an example. Let's use some practical examples to discuss this a bit further. If I take a loonie and I decide to toss the loonie, it is an experiment. It is a random experiment because the results could be a list of random events. Now, this experiment has a list of experimental outcomes. If I toss a coin, there is the possibility that I may see a head or a tail. And so then the sample space for tossing the coin, which is the list of all possible outcomes, is either a head or a tail. Let's take a look at another example of a random experiment. Let's say you inspect a vehicle or you inspect a part of an item. It could be that the part is defective or non-defective. And so these two possibilities is our sample space, the list of all possible outcomes. If I roll a die, for those of you who are involved in stuff like that, if I roll a die, what are the possible sample space? What are the list of possible outcomes? Is it I get a 1, a 2, a 3, a 4, a 5, or a 6? So this then gives us our sample space, all possible outcomes. Now, if I play a football game, I can either win, lose, or tie. And so I want you to pause a little bit and ask yourself, what are some examples of experimental random experiments, and what are their sample space? If I drive beyond the speed limit as a random experiment, what are the list of possible outcomes? What is the sample space? If you go higher than the speed limit, your list of possible sample space could be that you get a speeding ticket or you don't get a speeding ticket. Now let's take a look at another example here. So Bradley has invested in 2 stocks. He decided to invest in Markley Oil and Collins Mining. These are 2 companies that he invested some amount of money in. He determined that these are the list of possible outcomes of these 2 investments 3 months from the date of the investment. And so if he decided to invest in Markley Oil, this is the list of possible outcomes in thousands of dollars. He may get $10,000, $5,000. He may get nothing, which is 0, or he may lose $20,000. If he decides to invest in Collins Mining, the possible sample spaces are he will either win $8,000 or lose $2,000. So these represent the sample spaces. Now, every individual here, or every individual outcome in our sample space is what we call the sample point. So if he makes $10,000 from Markley Oil investment, the $10,000 alone is considered a sample point. It's the same for Collins Mining too. If he makes $8,000, that is a sample point. If he loses $2,000, that is also another sample point. But the entire list of possible outcomes is called the sample space. Now, to be able to represent the list of possible sample spaces in cases of where we are looking at two possible experiments, we usually try to create what we call a tree diagram. It's just a graphical representation of the multiple step experiment. And I will not be asking you to make a tree diagram, but when you look at a tree diagram, you should be able to understand what it's saying here. So looking at my Bradley's investment experiment as an example, he invested in two companies, Markley Oil and Collins Mining. Now, when we consider a combination of these two investments, what are the possible experimental outcomes? These are the possible experimental outcomes. He could either gain $10,000 in Markley Oil and $8,000 in Collins Mine. So when we combine these two profits, he makes $18,000. What we are looking at here is for the two different experiments, what is the total list of possible outcomes? If he invests $10,000, if he makes $10,000 in Markley Oil and loses $2,000 in Collins Mining, that is a combination of these two, and that at the end of the day, he gains $8,000. Now, another possibility could be that he will make $5,000 in Markley Oil and also gain $8,000 in Collins Mining, giving him $13,000. Or he could make $5,000 in Markley Oil and lose $2,000 in Collins Mining, resulting in a positive 5 for Markley Oil and a negative 2, which is losing $2,000 in Collins Mining, and the result will be $3,000. And so here we're looking at the list of all possible outcomes as a combination of these two investments. Now you can spend some time and look at how the combination will be for these other experimental outcomes as well. But then again, I will not be asking you to create tree diagrams anywhere, but it's important to understand. Now, the next thing I would like us to look at is how do you count for permutation? You see, permutation is a useful counting rule that helps us to count the number of ways we can arrange a particular set where the order of arrangement is important. Now, I usually like to do this as an in-person practical experiment, but if you have three different items, one is in the shape of a circle, the other in the shape of a triangle, and then maybe you have a square, and you have to arrange them in twos, what are the number of ways you can order them or you can arrange them if the order of arrangement is important? And so here we are looking at in twos, we can have a circle first and a triangle. This is one way we could arrange it. Or we could have a circle and a square. Or we could have a triangle. I'm sorry, that is not a triangle. Or we could have a triangle and a circle, or a triangle and a square. Another possible way of arranging where the order of arrangement is important could be that we could have a square and a circle, and then we could have a square and a triangle. And so permutation is talking about the number of ways three items could be arranged in twos, and this is important, where the order of arrangement is important. How we arrange it is important. This is a very useful counting tool, and in later discussions, you will see why this is useful. And so you will understand that if we have 3 items and we have to arrange them in twos, the number of possible ways we can do that is 1, 2, 3, 4, 5, 6. Now, obviously, if there are more items, it will take a while to be able to draw them out like this. And so we use this formula here to calculate permutation. If we have n items and we have to arrange them in set of R, then the formula is saying take the factorial of n divided by n minus r, or factorial. And so applying the same example here, what we are going to do is we are going to take n items to be the 3 shapes that we have, and we are going to arrange them in twos. And so n is equal to 3, r is equal to 2. Let's apply this formula here to see how we will be able to calculate it. Now, our permutation formula is saying take the permutation of n, which is 3, choose 2. Which means we are looking at 3 factorial over 3 minus 3 minus 2, all factorial. Now, let's pause a little bit and talk about the factorial notation. I'm sure most of you know what the factorial notation is all about. With factorial, what we are looking at is take the value of that number n and multiply by its subsequent preceding values until you get to 1. And so when we say 3 factorial, we are looking at 3 times 2 times 1. We take the value and then we multiply by the preceding numbers until we get to 1. And then we'll divide here by 3 minus 2, or factorial. 3 minus 2 will give us 1, and so 1 factorial here. How do we solve this? When I multiply the 3 by the 2, it gives me 6. 6 times 1 is still equal to 6. Divided by 1 factorial, we are looking at 1, and it's just 1. And so just like we showed you practically over here, when I have 3 items and I have to arrange them in twos, where the order of arrangement is important, there will be 6 different ways to arrange these 3 items. Let's look at other example of how we apply permutation. So suppose a portfolio manager has screened out 10 companies for a new fund that will consist of 5 stocks. And so here we have a total number of companies which is the number of items, and is equal to 10 companies. And we want to arrange them into portfolio where each portfolio will consist of 5 stocks, right? So we're going to arrange in 5s per portfolio. In how many ways can the funds be ordered? Now, it's important to note that it says here these 5 holdings will not be equal weighted, which means ordering will take place, which means the order of arrangement is important. And we said that when the order of arrangement is important, we are looking at permutation. And because we look at permutation, we'll apply the permutation formula, which says n factorial, which in our case is the 10 factorial, divided by n minus r, which is 10 minus 5, all factorial. Now, you can spend some time to do this at home when you have the chance, but 10 factorial is looking at 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that should give you 3,628,800. 5 factorial, when I subtract 10 minus 5, that will give me 5 factorial. 5 factorial is looking at 5 times 4 times 3 times 2 times 1. And that should be equal to 120. And so when we divide the numerator by the denominator, we are looking at 30,240 ways we can order these 10 companies into portfolios that consist of 5 stocks in each portfolio where the order of arrangement is important. Now, if this is making sense, I would like you to pause and practice with this. In class, we are going to spend some time to solve this, but let's take a look at the practice question here. You don't have to send me the practice questions. I would rather like you to just practice it, and then when we meet in class on Monday and Tuesday, we will compare answers. But the question here says that, say a company wants to build its warehouse network across the country. The company will commit to 3 locations out of 5 possible sites. Now, it's important to know that the bigger value in every permutation question, the bigger number is the N, and the smaller number is the R. And so they are committing to 3 locations out of 5 possible sites. Order matters because they will be built sequentially. In how many ways can they order this location? How many ways can they order 5 possible sites in 3? Now, apart from permutation, there is another useful counting rule called combinations. And so we are either looking at permutation as a counting rule or combination as a counting rule. These are the only 2 rules for counting that we will be looking at in this course. Permutation says, how many ways can we take N and order them in R where the order of arrangement is important? Combination, on the other hand, is saying in how many ways can we order or can we arrange N items in R, but the order of arrangement is not important. And so take a look at the difference between permutation and combination. With combination, the order of arrangement is not important. The way we order these items is not important. It does not matter. What does it mean? It means that if we don't have to have one before the other, they can be arranged in many different ways. Let's use the same example that we had before to show you the difference between combination and permutation. So I have 3 shapes: a circle, a triangle, and a square. In how many ways can I order these 3 items? In 2s. And so I have 3 items, and I'm going to order them in 2s. But this time, the order of arrangement is not important, which means I could have a circle and a triangle. I could have a circle and a square, and I could have a triangle and a square. And that's basically it. The order of arrangement does not matter. It doesn't matter if triangle comes before a circle. It's the same thing in combination. And so when we have 3 items and we have to order them in 2s, this is the number of ways we can order them. Now let's try to prove this using the combination formula. Our N, which is the total number of items, the bigger number is 3. Our R, which is the number of ways we can arrange them, the number of sets that we can have them, is 2. So using the combination formula here, we will have 3 factorial over 2 factorial into bracket 3 minus 2 or factorial. How do we solve this? 3 factorial, we're looking at 3 times 2 times 1. 2 factorial is looking at 2 times 1. And then 3 minus 2 factorial, basically it's just 1 factorial, and so that will be 1. When I simplify the numerator, 3 times 2 times 1 will give me 6, divided by 2 times 1 times 1 will give me 2. Now I can simplify this further and divide the 2 will go into 2, 1, 2 will go into 6 3 times. And so here, the number of ways I can arrange 3 items in twos where the order of arrangement does not matter, will be in 3 ways. And that is what we had right over here. If we have 3 items and we have to arrange them in 2, 3 is the number of ways we can arrange these items. Now let's look at an example. And again, you can practice this as well. But suppose you just got a free ticket for a boat ride and you can bring only 2 friends. Unfortunately, you have 5 friends you want to come along. How many group of friends could you take with you if the order is irrelevant? See, it's important to always think about this. Is the order of arrangement relevant or irrelevant? If it is irrelevant, then we are looking at combination. If the order of arrangement is important, then we are looking at permutation. And so in our case here, our N is 5, our R is 2. We apply the same formula and we will get 10 number of ways to choose 2 friends out of 5 if the order of arrangement is not important. Now there's another practice question here. You can pause this video, try your hands on the practice question, and then in class, when we solve it together during our discussion, you will compare answers and then you can ask me questions on that. Okay. Now, just before I bring this session to a close, I'd like us to quickly look at some basic rules when it comes to assigning probabilities. We've already said that probability can be between 0 and 1 inclusive. It can never be less than 0. It can never be more than 1. Now, the second rule of probability is if we have an experiment, the probability of the sum of the probabilities of the individual outcome should always be equal to 1. And so let's take, for example, I toss a coin. If I toss a coin, what is the sample space? Our sample space is either I get a head or I get a tail. What this rule is saying is that the addition of the probability of these 2 possible outcomes should be equal to 1. How do we prove that? If I get a head, there's a 1 over 2 chance that I get a head, and there's a 1 over 2 chance that I get a tail. And so the probability of getting a head, let's represent that as P of H, plus the probability of getting a tail, let's represent that as P of T, will be half and half. And that should be equal to 2 over 2, which is 1. And that's what this rule is saying here. And so irrespective of the number of outcomes, when you add them up, they should always be equal to 1. The other rule of probability, this is the different types of probability that we can look at. The classical method of assigning probabilities, the relative method of assigning probabilities, and the subjective method of assigning probabilities. In this course, we are going to look at the relative method of assigning probabilities. And you may have done this when we were calculating relative frequencies for the relative frequency table or the frequency table distribution. And so you are familiar with this, and that's what we are going to be looking at when it comes to probabilities in this course. The classical method is mostly used in things like gambling, where we assume equal chances in all possible scenarios. The subjective method is one that is based on personal opinions, and because this is statistics, we don't deal with personal opinions. So we are not going to use the subjective method. On the other hand, we are going to use the relative frequency method of assigning probabilities. Now, talking about the relative frequency method, what are we looking at? We are looking at situations where for every value we assign in terms of probabilities is based on how many times that event occurs. Let's take a look at this example here. So Lucas Tool Renter would like to assign probabilities to the number of car polishes it rents each day. Office records show the following frequencies of daily rentals for the last 40 days. So for the last 40 days, this is the frequency of daily rentals. For a number of polishers rented, zero number of polishers rented, we counted 4 days. So there were 4 days where they couldn't rent any polisher. There were 6 days that they rented 1 polisher, 18 days that they rented 2 polishers, 10 days that they rented 3 polishers, and for 4 polishers rented, it only occurred 2 times. And so here we have our frequencies, and this is the number of polishers that were rented. What we want to do with the frequency method is we are going to base on the frequencies to determine the probability that 0 polishers will be rented, 1 polisher will be rented, 2 polishers will be rented, 3 polishers will be rented, and 4 polishers will be rented. How do we apply that? To apply the relative frequency method is a very simple and straightforward approach. Take the value or the frequency for each observed count and divide by the total number of frequencies. So to calculate it, I will take, to find the probability of 0 polishers rented, I will take the 4 divided by the total number of frequency, which is 40, and that will give us a probability of 0.10. It's the same for all the others. Take the value. So if I want to find the probability that 1 publisher will be rented, I take the value, the frequency, which is 6 number of days, divided by the total number of days, which is 40. It gives me 0.15. Now, in this case, we are going to look at some possible events and their probabilities. Event basically is a collection of sample points, and the probability of an event occurring is the number of events, the number of outcomes in that event divided by the total sample space. Let's take a look at an example here. And then maybe after that, we will pause and continue in another session. Let's say a street gambler tosses a fair die with the following probability distribution for different outcomes. Let's find the probability that the outcome is an even number. So our event here is that we are looking at even numbers. If you roll a die and we are looking at event that is an even number, these are the total possible outcomes for even numbers. Is it that you get a 2, a 4, or a 6? And so to find the probability that the outcome will be an even number will be the number of even numbers we have here, which is 3, divided by the total sample space. Now, if I roll a die, my total sample space will be 1, 2, 3, 4, 5, and 6. And so my total sample space is 6. If I want to find the probability that I'll get an even number, is the probability of E equal to 3 out of 6. 3 will go into 3 one time, 3 will go into 6 2 times, which is the same as 0.5. And so there is a 0.5 chance that if I roll a die for the 6 possible outcomes, I will get an even number. Okay, I want you to spend some time, and it's not here on the slide, but as a practice question, I want you to spend some time and think of what are the possible outcomes, or what is the probability that it will be, the event will be an odd number. So if it's an odd number, what is the probability that the event will be an odd number? And then if you're able to practice this, that would be great. Okay, let's pause here and we'll continue with the rest of the slides in another section. Thank you very much for joining me. See you in the next lecture.